Swayam Prabha. Digital India. Educated India.
Welcome to Module 50 of Point-Set-Topology Part-I. So let us continue the study of half-starsness along with compactness and so on. Last time we gave some applications to function analysis, nonlinear spaces. In particular, we showed that every nonlinear space in which the unit sphere is compact, then it is finite dimensional. Of course, we did many other things, like we showed that the entire of Rn, no matter which norm you take, is a cone over the unit sphere. When you change a norm, the unit sphere changes, but the cone over the unit sphere is always homeomorphic to the underlying linear space, Rn. So this is what we have seen. So let us continue that. As a consequence of the discussions last time, we also get the following theorem. Let S and D denote the unit sphere and the unit disk respectively with any norm on Rn. Remember, if the norm we have taken the L2 norm, then I have a different notation. I have special notations for this. This is the general notation for any Rn. Then they are, means S and D are respectively homeomorphic to the standard Euclidean sphere and the standard disk. Okay, so this is a consequence of our discussion last time. However, let us just go through the proof carefully. What is finally involved in it? Okay, fix any arbitrary norm on Rn. We know that it is continuous and non-vanishing on the standard unit sphere Sn minus 1. The norm is a function into R, right? R plus actually. Restricted to Sn minus 1, we already established that it's continuous. Now, what do I mean by continuous? Now, I can take the standard L2 norm on Rn. With respect to that, this function, which is a norm on Rn, is also continuous. This is what we have seen. In particular, on the sphere, it is non-vanishing. Therefore, 1 by norm x is also continuous. Okay, so it follows that if I put lambda x equal to x by norm x, then this lambda is from Sn minus 1 to S is continuous. You see, this you have to be careful here. This is the new norm. Sn minus 1 is the standard norm. Okay, so L2 norm. L2 norm is 1 doesn't mean that this norm is 1. So I have to divide by this so that I get into this capital S here. Okay, so x going to x is continuous. 1 by norm x is continuous. The product will be continuous. Okay. Likewise, if we take mu x equal to x by L2 norm now, so the role will be reversed now, domain and codomain. then mu will be continuous from S to Sn minus. What is easy to verify is that lambda and mu are inverses of each other. Okay. Therefore, each of them is what? A homeomorphism. One is the inverse of the other. Once that is the case, you can take the cone over Cs minus 1, which is D, is homeomorphic to cone over Cs. Okay. This is Dn here. This will be the D here. So this also we have seen. That is the thing that we have seen last time. Okay. The first one Sn minus 1 is Dn. The second Cs is the unit is with respect to the extra norm, usual norm, unusual norm. This is the usual norm L2. So once two spaces are homeomorphic, their cones over them are also homeomorphic is one of the theorems that we saw last time. So now let me take a genuine example here, which you may all be interested in. Maybe I will try to first stop. I may have to stop this presentation and then do something. I wanted to show you a piece of string. Can you see that? What does it represent? I mean, how do you represent this by a mathematical object? So you can either say this is a closed interval when you include the endpoints of the string, or an open interval or a half open interval. There is no other way to represent a half open interval or open interval or closed interval. All of them are represented by string. I have to tell me what it is. Okay. So this is, you can say it is 0, 1. When you identify just 0 with 1 and nothing else, what do you get? You will get some object like this, which is a model for S1. Okay. Actually, the model is S1 is a model. This is, this is the object, whatever. It doesn't matter whether it is like this or like this and so on, up to homeomorphism, this is S1. So all this we know that, a layman will understand that this is a circle. Now, mathematically, we want to rigorously say that identifying the endpoints of 0 and 1 gives you S1, right? So that is what I want to rigorously prove now. So that was my main interest here. Okay. Okay, so let me go back to the slides. Okay, so let us do this business. Namely, let us prove that the quotient of the closed interval 0, 1 by the identification, namely the endpoints 0 and 1 are identified, is actually S1. Okay. So I will denote X by 0, 1. Okay. I don't have to take any other interval because they are all homeomorphic to 0, 1. Any closed interval is homeomorphic to 0, 1. That we know already. So define a relation. 0 is related to 1. 1 is related to 0. X is related to X for every X. So this is a equivalence relation. Okay. There is no other rule here. Okay, now let Q from X to X by R be the quotient map. This X by R, which is quotient topology, we want to show that is homeomorphic to S1. Our task is to show that it's homeomorphic to the unit circle. Okay. To get a homeomorphism, we observe that whenever you have a quotient space, what you do is you construct the function on X itself, on the mother space itself. Okay. But now what we observe is X is compact, therefore X by R is compact. And S1 is Hausdorff. Then one of the theorem that we have tells you that if you have a continuous bijection, then it will be automatically a what? Homeomorphism. So that is what we are going to exploit here. Okay. But now to construct a function from X by R to S1, we appeal to this lemma which we proved long back. So what was this? When you have a quotient map X to Y, okay, given any function f from X to Z, there is a unique function f twiddle from Y to Z, such that f twiddle composite Q is f if and only if this happens. Okay, whenever 2 points are identified by Q, the same thing should happen to the function that you are interested in. That should also identify those 2 points. This is the condition. Of course, now our notations are slightly different. X to X by R is the same, that is Q. I want to get a homeomorphism here. Okay, to get a map here, I should have a map here first of all, such that Gx is equal to Gy. Thus, whenever X is not equal to Y, implies only X and Y are, the pairs 0, 1. Either X is 0, Y is 1, or Y is 0 and X is 1. That is an unordered pair is the same. Okay, why I have put this one? Because finally I don't want any more identification here. I want this one to be injective. Okay, I want first of all this function, so it must have 0 and 1 should be gone to the same point here. So G must have that point. G of 0 must be G of 1. Okay, otherwise there is no equality. I mean, X is not equal to Y. Okay, then Gx will be not equal to Gy. So such a map is readily available to us already. This you don't have to hurt for it. Take Gt equal to e power 2 pi it restricted to 0, 1. When t is 0 or t equal to 1, it is the unit of S1. And everywhere inside, it is injected. So when you come down here, you get a continuous function which is injective. But G is already surjective, so this is surjective also. So this becomes a homeomorphism because X by R is compact and S1 is Hausdorff. Let us go to some other example now, namely the projective space PN. We haven't studied much of it, but we have studied its definition. So I will recall the definition. So projective space PN, the real projective space is called. There is a complex version also, as you may appreciate. It's defined as a quotient of non-zero vectors in Rn plus 1 by the diagonal action of R minus 0. Namely, R, comma, x0, x1, xn goes to Rx0, Rx1, Rxn. So it's also scalar multiplication, you may say, diagonal action or scalar multiplication. Okay. We have then claimed that this quotient map, when you restrict it to Sn, namely unit vectors, is also a quotient map. That time it was an exercise for you. Now, this claim easily follows from our earlier theorem. Why? Because now Sn is compact. Okay. And what we have shown is that it's a closed map. Okay, so this will be also a quotient map now. Okay, Sn to Pn, it's easily seen that it is surjective continuous map, but now because Sn is compact, the function will be a closed map. Every closed subset is compact, and what? The image of a compact is compact. A compact subset of a Hausdorff space is closed. So that was the theorem. Okay, so you can use that. It follows that Sn2 Pn is also a quotient map. Of course, it is not bijection. So it otherwise should be homeomorphism. Here, antipodal points x and minus x are mapped to the same point. Okay, this quotient is easier to understand. Namely, it is under the antipodal action. X goes to minus x. And both of them, x and minus x, go to the same point. Okay. So, in particular, why I took this example, now it will follow that Pn is compact. Okay. We didn't have that one. That Pn is compact here. The only thing we had to bodily verify is that Pn is Hausdorff, which is not very difficult to verify. The entire exercise here, you don't have to worry. You have to just say that Pn is Hausdorff. That much you have to verify. Then only this theorem can be applied. Okay. So now I would like to take a different game here. Recall that we had defined an embedding long back, maybe, of a topological space into another space Y. What is the meaning of an embedding? It means a continuous injective map such that when you restrict f from x to fx, not the whole space Y, this is a homeomorphism where fx is given the subspace topology from Y. So that was the definition. Okay. Beyond definition, we have not done much. Now at least we will have some examples here. So now I specialize to the case wherein n is equal to 2. So look at the projective space P2 of dimension 2, which is quotient of S2 by antipodal action. Okay. What I want to do is, I want to explicitly write down a embedding of S2 inside R4. Sorry, embedding of P2 inside R4. S2 is embedded in R3. S2 is a subspace of R3, right, by definition. But P2, I would like to embed inside R4. Why? Because for some reason, I am not able to embed it inside R3. Actually, a deeper theorem in algebraic topology will tell you that you cannot embed P2 inside R3. Okay. Notions such as orientability, etc., have to be studied to understand that. Okay. So to get such a function, what I should do? I should construct a function from S2 to R4 such that fx is equal to fy if and only if x is plus minus y. Then I will get a map f bar from P2 to R4. Okay. If this is if and only if, when you come here, it will be already injective mapping. If fx equal to phi, if and only if x is plus minus y, then the corresponding function f bar from P2 to R4 will be injective. Once again, this is compact, that is Hausdorff. So f bar from P2 to f of P2, f bar of P2, that will be homeomorphism, which means f bar is an embedding. The task is to find a function f from S2 to R4, which has this property. Points are mapped to the same point only if they are antipodal, otherwise they are distinct. This is what I have to do. Okay. So hunting around various examples, It turns out to be a pleasant surprise that we can do it with a quadratic embedding. Namely, whenever you have plus minus x going to the same point, so the natural thing is to look for quadratic functions. X squared, y squared, x plus y squared, x squared plus y squared, and so on, the combinations. So they will have this property, right? Homogeneous quadratics. And a hunt like that is actually giving you that. So naturally you can try x, y, z are three coordinates here. Remember, I am only interested in inside S2, okay? Not the whole of R3. This will make sense in the whole of R3, no problem, because they are polynomial functions. Look at xy, xz, and yz. These are obviously three easiest things. Of course, I could have taken x square, y square, z square, but there will be a problem. Suppose I take x square, y square, z square. Would it work? Finally, even xy, xz, yz also doesn't seem to work. I have to take one more coordinate, namely I pick y square minus z square. Okay. After that, it is a matter of checking that when you pass down to P2, obviously, so if you replace each xyz with minus x, minus y, minus z, then this side RHS here remains unchanged. Okay. Don't just change x to minus x. That is not the idea. That is not required. When you change minus, it is minus x, minus y, minus z. So that is the antipodal point of xyz. So that will go to the same point. Therefore, this will give you a function f bar from P2 to R4. Now you have to see that function is injective, that's all. Okay. So that part I'm going to leave you as a pleasant exercise. Verify it. Okay. I will go to another interesting example. Once again, this also something like a non-orientable surface. P2 was one such, this also not. This also cannot be embedded in R3, but similar efforts to P2 seem to work here also, and we will get an embedding in R4. Okay. So first of all, I have to explain what is this Klein bottle K. Okay. It is a quotient, a double quotient, a 2-to-1 mapping is there of the torus S1 cross S1. Okay, what is the action? Action is important here by the diagonal action, okay, of minus 1 plus 1, Z2. Okay, so diagonal action has to be taken very carefully here. UV going to U inverse and minus V. The one coordinate you take inverse, multiplicative inverse, another coordinate you take additive inverse. So S1 minus 1 is just, this is the antipodal action. So this one is the multiplicative inverse. Okay. First of all, let us work out a geometric way of obtaining Klein bottle out of the above definition. Suppose I take this as definition. Okay, this is not a standard definition, but now let us try using the well-known geometric way of getting a Klein bottle out of the torus. The torus S1 cross S1 is defined as the quotient of a rectangle I cross I, wherein the four sides are identified in a particular way. The 0, 1 cross 0 is identified with 0, 1 cross 1. So that is the opposite side, right? in the same oriented fashion. Similarly, 0 cross 0 comma 1 will be identified with 1 cross 0 comma 1. Okay, again the opposite sides. That is the identification here. This is the square 1 cross 1. So this bottom thing goes to the top thing here. See the double arrow and double arrow are indicating that. This is a triple arrow on vertical lines. They are identified. This is the identification. The arrow tells you how the identifications are done. For example, here an element can look like t comma 0. So where it will go, it will be identified with t comma 1. Similarly, 0 comma s will be identified with 1 comma s here. Okay. So this is the once you identify this, you get a torus. But to get the Klein bottle, I have to do some more identification. Because on the torus, I have an action u going to u inverse and v going to minus v. Right? So that is what I have identified here. I have tried to put it here. Okay. So what happens is, if you look at this arrow, the bottom line here, this will get identified with the middle one dot 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 1 in the opposite direction. These elements will be there all the time. There is no identification there, okay? But what further identification? What happens is, this will be identified that part. Okay, this is getting identified this way anyway. All right, and this is getting identified anyway. All these points here, they will be identified with corresponding points here. Something here will come here and so on in the opposite direction. Around the half of this one, there will be self-identifications. There will be no identifications, within the interior of this half rectangle. Everything above will be identified some point here. Therefore, the upper half part of this rectangle is unnecessary. So I have cut it off and represented a half rectangle here of the original one. Now the identifications of this one will give you Klein bottle. So this is the geometric way. Okay. To justify all these things rigorously, you have to write down formula. That is the only way. Okay. So that's what we have to do. Okay. So this is the diagonal action u comma v going to u inverse comma minus v. Since u and v are now representing elements of S1 cross S1, but I am representing them on the plane only after identification, namely t going to e power 2 pi I t, you will get an element of S1. So what is the corresponding identification of this one in terms of real coordinates? So I have to convert that, and that amounts to the following thing. T, if you represent t, the element u is represented by t means what? U equal to e power 2 pi I t. Okay. So this v is represented by s means v equal to e raised to 2 pi I s. That is the meaning of this. So when you get that, u inverse will be represented by 1 minus t. Okay. Whereas minus v will be represented by s plus half. Okay. This is very easy. You apply e power 2 pi I t, what happens? E power 2 pi I 1 minus t is just what? It's just the inverse of e power 2 pi I t. And this is a minus of that, because half of 2 pi I half will be pi I. So e raised to pi I is multiplied by minus 1. Okay, so that's all I have done. And the second part is, see, t, this is in the t first half. In the second half, t comma s will be 1 minus t comma s minus half, because plus half goes away out of that one. So I have to take half less than 2 less than 2. I have to take s minus 1. So these two are the same effect, but the actual map will be s minus 2, because I have to be within a 0 less than 1 less than half. If s is bigger than half, s plus half will go out of 1, right? So that's why I have to write like so. The entire quotient map can be restricted to s equal to 0, 1 cross 0 half. You don't need the second part at all, this part. Now, in the interior of S, there are no identifications. Let us check what are the identifications on the boundary. Okay. So this is what I have already done. The two vertical sides have to be identified as indicated by the arrows. The lower horizontal arrow 0, 1 cross 0 gets identified with 0, 1 cross half. In the reverse direction, via the map t comma 0 going to 1 minus t comma half. I have to just understand what is happening here when you put s equal to 0 and s equal to half. Okay, so this is what happens. Thus, the paper model of Klein bottle is given by the rectangle on the right hand side here in the picture which I have shown. Paper model means you have to indicate how you are going to identify the boundaries. That's all. Okay. So this is the explanation of how to construct a paper model of Klein bottle. All right. But now I go back to my definition of the Klein bottle as a quotient of S1 cross S1 by the identification, namely u comma v identified with u inverse comma minus v. Okay. Once again, this time I am denoting these A, B, C, D, etc. inside R4 itself, because S1 is embedded in R2. So S1 cross S1 is embedded in R4. From R4 to R4, I want to take a map such that whenever 2 points are identified, they are going to the same point. If and only if. So that is the same technique. So what do I do? Take A, B, C, D. Remember, these are all A square plus B square is 1. C square plus D square is 1. That is the condition in R4 for this to represent S1 cross S1. Okay, let it go to 2 plus A, C square minus D square, 2CD into 2 plus A again, then BC, BD. Okay, and take its restriction on S1 cross S1. This map is completely defined on the whole of R4. But I am only interested in S1 cross S1, means put A square plus B square equal to 1 and C square plus D square equal to 1. That's all. So once you put that, you can think of A, B, C, D as some sine theta, cos theta, sin theta, and cos psi, sin psi, something like that also you can try to do. Okay, G2 action in this notation corresponds to A, B, C, D, right? AB gets A minus B, it's inverse. CD goes to minus C minus D. So it is negative. No, now it is a matter of straightforward verification to check that F factors down to define a continuous injective map F bar from K to R4, which is just by the similar argument is an embedding. Okay. How I got this one? If you look at 2 plus A, C square minus D square, 2 plus C, D. If you write A is cos theta, sin theta, cos psi, sin psi, up to here, the third coordinate, it gives you an embedding of S1 cross S1 in R3. So you put one more coordinate here to get an embedding of R4 of the project of the client bottom. Okay. So this 2 plus A corresponds to, the center of one of the circle is shifted to 2, 0. See, and this is 2 plus A, 2 plus A. And then this is cos 2 theta, and that is sin 2 theta. So you just take, instead of theta, 2 theta, so that will give you, when you help to give you map into P2. That is a slight modification there. Okay. Yeah. So we have done something nice today. Let us stop here. Next time we will take 2 more properties which are very, very important. Again, the separation properties, regularity and normality. Thank you.